Hi, my name is Alessandro Scovini, and I'm here presenting the work titled Damage Assessment of Carbon Fiber Reinforced Polymer Laminate Plate Subjected to Close-Range Blast Loading and Hydrocode Methodology Validation and Case Study. Co-authors are Luca Lomazzi, Marco Giglio, and Andrea Manes. In this slide, the presentation summary can be seen. First, the topics and the motivations of this work are introduced. Then the case study this work is based on is presented, together with the methodology we've employed and used to carry out the numerical analysis. Then the results are going to be presented and discussed and compared with those from the case study. Finally, the conclusions are drawn. This work focuses on composite material that are being extensively used in military equipment and assets. In this field of application, composite structures are subjected to many risks, and the one we are focusing on is attacks from explosive ordnance. This loading condition is found from us to be scarcely represented in literature, both in terms of experiments then also in terms of numerical or analytical simulation. So what we wanted to do in this work is to investigate the damage caused by blast loading on composite target using numerical simulation. This work focuses on replicating damaging in a carbon composite panel using the commercial software LSDyno. The experimental tests considered to compare with the FEM model are taken from the paper of Gargano and co-authors that is cited in the slide. The paper presents the detonation of a 100-gram spherical Type 4 plastic explosive charge at a 0.4 meter standoff distance from a flat quadrangular composite plate. The composite is constituted by plain carbon woven fabric, made by 7 plies stuck one on the other, with the same orientation, all the plies with the same orientation, being a 090 pattern. The composite plate is fixed in a steel frame lined with the APDM 414 rubber form. The size, the plate has a quadrangular shape, as said, with a 275 millimeter side, while the steel window, still quadrangular, has a 250 millimeter side. In this slide, the two methodologies used are presented. First, the pure Lagrangian approach was used. It consists of modeling the structure with Lagrangian element and applying the blast pressure with an empirical analytical equation, the Kingery-Bulmash equation. This method is generally addressed as the Conweb method. Then, the fully coupled Euler Lagrangian approach was used. It consists of modeling the structural parts, so target, the frame, and the rubber with the Lagrangian elements, while the Eulerian domain represents the air. The shock wave is initiated in the air domain by loading its upper surface, which is represented with the red arrow in the slide, with the analytical prediction from the Kingery-Bulmash equation from the Conweb method. And this results in the possibility to significantly reduce the computational effort by this analysis, because it allows not to model the whole Eulerian domain that should also contain the explosive. These two methods represent a step forward and a novelty with respect to the case study this work is based on, because in the work of Gargano and the other authors, they applied the pressure as a load calculated with the Conweb method. While in this case, for the pure Lagrangian approach, an LSDyno keyword allowed to apply directly the Conweb method, so the pressure is exerted on the surface, while the fully coupled Euler Lagrangian approach allows us also possibly to model the fluid structure interaction. Regarding composite modeling, the composite material was modeled applying a macro-homogeneous discretization. Namely, each ply was defined with a single layer of element using the LS-DYNA software. The woven layers were modeled using a fully integrated hexahedral elements having a characteristic dimension of 2 mm. The material model MAT54 was used in LS-DYNA, and the damage initiation criteria considered is based on hashing criteria, with the modification accounting for the fact this material is woven. In this slide, the equation governing the failure criteria are presented. The composite material was modeled also accounting for interlaminar damage, namely delamination. Delamination was accounted with a contact interaction that is implemented in LS-DYNA that connects nodes belonging to adjacent layers. This contact interaction failure is governed and features a failure criterion that has a quadratic form. The criterion accounts for normal stresses and shear stresses both in planes and out of planes, and its stress, normal and shear, is divided by the maximum allowable stress. In order to reliably represent the loading condition, the whole experimental setup was modeled because it was found that the boundary condition dramatically influences the results. So steel was modeled as a purely elastic material, while the foam was modeled with the material C57 in LS-DYNA, which is a material model dedicated to highly compressible low-density foams. Moving to the result and discussion section. In this slide, the results in terms of pressure and deflection are presented. In the first plot on the left, the pressure exerted on the composite plate is showed for the CEL and the Lagrangian approach. It can be seen that the Conway method, the red line, reaches a higher pressure. This results, in fact, in the plot in the right, in a larger deflection for the composite plate that, in fact, reaches almost the experimental observation. The blue line, instead, from the CEL approach, reaches a lower level that can be still considered to be acceptable. In this slide, the results in terms of interlaminar damage is shown. In the first picture on the left, the experimental results from the paper of Gargano is shown. The black carbon plate features a red dashed lines that underlines the area where where damage was observed. The picture on the right showed the numerical results from their analysis. The picture was addressed in the paper as a ply rupture, and the ply rupture is defined in blue in the image. On the right, we can see the results from the pure Lagrangian and the CEL approach analysis we carried out. Again, the area in blue represents the elements where the failure condition was met. In the uppermost ply, so the two images on the top, we can see that we have severe compression damage, though the same direction are found in this image. In fact, we can see somehow an oblique line and direction on the top, as well as damage that started on a grippage area and propagated through the middle. Moving to the outermost ply, we can see that tensile damage is also present that instead was missing in the uppermost, or anyway upper plies. And at the same time, compression damage is also present in the outermost plies. The results from the two analyses, however, are very similar, so this also sort of confirms the reliability of these two methods. In the bottom left, we can see we reported an image from the paper of Gargano where they showed a through thickness crack that propagated during blast, and we can see that this feature also is present from the numerical analysis I carried out, both the pure Lagrangian and the coupled earlier Lagrangian. Here, the results for interlaminar damage are presented. First, on the left, the experimental picture from the paper of Gargano is showed. The picture was taken with ultrasound technique. Next, the numerical analysis result from their paper is showed for the sake of comparison. In this case, they also got some discrepancies compared to the experimental one. Moving to the right, the results from the pure Lagrangian and CEL analysis are presented. In our analysis, we mostly saw the lamination occurring in the corners of the plate. In fact, in this area, we noticed that wrinkles were occurring close to the corner, and this area was in fact delaminated. It must also be pointed out that between the fourth and the fifth slide, so in the middle of the composite panel, severe delamination occurred, and this was also seen as the composite plate was basically splitting in the middle. This difference and this result is likely to be related to the boundary condition and the definition of the properties of the other materials involved in the simulation. Finally, moving to the conclusion, the presented methods to simulate the blast loading are validated and efficient to represent this event. In addition, the results in terms of pressure and composite plate vertical displacement are found to be close to those reported in the paper this work is based on, the paper from Gargano, while some discrepancies are found in the damaging of the composite lamina. So further analysis are foreseen in order to improve the damage representation by investigating, for instance, other material model for interlaminar damage, and also perhaps by changing the method to address interlaminar damage, for instance, like cohesive elements. Also, to conclude, blast secondary effects can possibly be considered in order to obtain a more comprehensive description of the phenomena occurring. Thank you for your attention.